In this video, I want to talk about a way to establish bounds for what we call the remainder of a series. So let's start there. Let's start by talking about the remainder of a series. So here I have a series that converges to a number s. And more than that, the nth term formula is equal to a function that's continuous, positive, and decreasing. Okay, well, what do I mean by remainder? Well, if this series converges, what it means is the sequence of partial sums converges. So as I keep adding on more and more terms of the series, this list of numbers gets closer and closer to s. Another way to think about that, especially for large values of n, is that s sub n should approximate the value for s. But never quite getting there, because I'm always missing some terms if I'm at the nth partial sum. How far off I am is called called r sub n. That's the remainder. Simply take the sum, take away what we're approximating it with, the nth partial sum. So that's r sub n, the remainder, if I'm thinking about that nth partial sum as an approximation for s. Okay, well, what does that mean? Well, if I think about the fourth partial sum, it means that the remainder would be all of the terms added together past a sub 4, a sub 5 plus a sub 6. All the terms I haven't added on yet. Meaning this remainder is also a convergent series. An infinitely long sum of numbers that have to be converging to something. This is what I want to try to get bounds for. That's also going to give me a way to approximate s using an interval of values, which will be a very powerful tool. But for now, I just want to talk about a way to approximate this remainder if I have a series based on a very well-behaved sequence. A sequence that's equal to a continuous positive decreasing function. So let's think about that case. Let's just imagine that I have some convergent series whose terms are generated using some positive, continuous, decreasing function like that. I only want to draw the end of the sequence. So imagine a large gap on my x-axis, like, I don't know, 1 through 1 billion happens in there, and then the end of the series happens here. So imagine starting at n, and then n plus 1, and then n plus 2, and we're going to imagine these are evenly spaced, just n plus 3, counting out by 1 every time here at the end of the series. I'm going to just do that again, maybe try to make it a little neater here on the x-axis. N plus 1, n plus 2, n plus 3, and we just keep counting out like that. All right, so I want to think about those remainder terms. And so what I'm going to do is I'm going to think about each one as being a little rectangle. So my sequence is giving me these dots. Right, if I think about that nth term formula, right, just the sequence of numbers this series built from a sub n and a sub n plus 1, going out like that. But to think about a series, I need to be adding together a bunch of values. And in this diagram, I can do that by thinking about these areas. Imagine continuing to do that. Because I plug n plus 1 into the function, and I get a sub n plus 1 times the width of 1. That little rectangle's area is a sub n plus 1. And that's true about all of these. So if I add together all of these areas in this tail, that is r sub n, right? That's my remainder, right? That's what I wrote down here. So now I have a visual representation for it. But when I look at those rectangles, my brain's saying, hey, that's an upper sum. And since it's going on forever, it's an upper sum for some improper integral. Well, what improper integral would it be an upper sum for? Well, it's the integral starting at n plus 1, where that rectangle starts, going to infinity of this function f of x. Well, the series itself is an upper sum, so I can establish this inequality. This improper integral is less than or equal to my remainder. All right, well, that's a way to get a bound. I know how to evaluate improper integrals. I know my remainder would be larger than this one. Well, now I'm hoping to get a spot where my remainder, or excuse me, a value that my remainder would be less than, and then I've done what I set out to do. So I'm going to draw another diagram, thinking about the same series, same continuous positive decreasing function. We'll pretend that's exactly the same. Same spots here on the x-axis. And this time, instead of drawing a set of rectangles that would correspond to an upper sum, I'm going to draw a lower sum. And again, that's a sub n plus 1, right? I go up, I hit the function, and I have a rectangle with a length of 1. These rectangles, well, that's r sub n, right? That's my remainder. Well, if I shade forever, at least. This looks like a lower sum. What's the lower sum for, though? Well, an improper integral this time starts at n and goes to infinity. So that's the actual area under the curve. Those rectangles are a lower sum. I think I've set out to do what I started to do. I have the inequalities that I wanted, right? R sub n, I now know is less than or equal to this improper integral. And it's greater than or equal to this one. Well, let's try that again. That marker is clearly dying. I've used it too much, apparently, and I keep trying to use it, so we're just going to put that away and start over again. Those are the bounds I was looking for in those improper integrals. Now, very formally written out, we have this statement. The bounds for the remainder in the integral test. Suppose that I have a sequence a sub k of positive terms with a sub k equal to f sub k, where f is positive, continuous, and decreasing, for the x's past some value n, and that the series converges to s. Then the remainder, r sub n equals s minus s sub n, satisfies the inequalities we just derived. So that's a very formally stated theorem, and it's absolutely true. But what's even better about it is I can do a little arithmetic here in the middle of it. See, I have an improper integral that I know is smaller than my remainder, and an improper integral I know is larger than my remainder. But I also know what the remainder is equal to. It's s minus s sub n. And if I'm dealing with a series I know converges, s is what I probably actually want to be approximating. And if I just add s sub n to all three pieces, I get this statement. And this actually gives me a tool by which I could approximate s, or give a range of values where the true sum has to live. I calculate the nth partial sum, and I add to it this improper integral to get a low bound. I add to it this improper integral to get an upper bound. In our next video, we're actually going to go through all these ideas in a video.